Okay, so we are going to probably finish up Chapter 2 today. Probably do 2 sections of Chapter 3, and then we will have the next test. So it probably won't be next week. It'll probably be the week after next. I read this interesting article today during my lunch, while I was eating my lunch. And so I'm sharing this with you just because I think it's interesting. It actually has applicability. I just got to find the article now. I might send you the link so you can look at it. Anyway, they're happy playing their video games. Okay, here to the math stuff. So the basic idea here is we're going to look at the results of surveys, and we'll start with a simple survey, and then we're going to use Venn diagrams to take the information that's given and then be able to take the filled in Venn diagram and then answer other questions about survey data. So surveys are putting people's preferences into sets, into groups. And what we're going to be talking about, we don't care specifically about who in the survey decides they like one thing or the other. We're just interested in how many people responded in a certain way. So we're going to populate our Venn diagram with numbers. So it's using the stuff we learned last time. So here's an example of it's problem 19 in your book. And so the question is, they've done this survey of Joe, and it turns out that Joe is a music producer and writer. And so when they asked him, how many songs have you written and produced? He said 3. How many have you written? He said 2. And how many have you produced? You have 7. And if you add these up, it doesn't equal 9 because there's this crossover. There's the ones that he wrote and produced. So what we can do is we can populate a Venn diagram using this information, and then we can answer these additional questions that maybe were answerable based on the original data. So we're going to draw a Venn diagram, which consists of our rectangle. And because we have 2 categories, we have things that he produced and things that he wrote, we just need 2 circles to represent those 2 sets. So I'm going to, and because there is some crossover, because we do have a case where he wrote and produced, we overlap the 2 sets. And I'll use a letter to designate each response. One is he wrote, and one is he produced. And where they're overlapping is where he wrote and produced. So we'll start with the one that involves the and statement, because that's an overlap, and so this area is overlapping. So it says he wrote and produced 3 projects. So we know that we put the number 3 in there. That says that according to the Venn diagram, there are 3 songs which overlap, which means that they're an and statement. And so that's how you start. Now, what we're looking to do is find a number to stick in here, which applies to the songs he wrote but didn't produce. But that's not what that's not the question. They didn't ask that directly. So we have to figure out what number goes in this moon-shaped part based on this information. So it said he wrote a total of 5 projects. So the number of projects that he wrote has to be represented by the sum of these 2 areas, because these 2 areas, the football and this little moon shape put together create a circle. So if the total in the circle has to be 5, and I've already gotten 3, that means that 2, I put a 2 here, which means he wrote 2 but didn't produce it. And when you add everything in this circle together, 2 plus 3, you get the number he wrote. Likewise, he produced 7 projects. So I know that inside the produced circle that I have to have a total of 7 projects. I've already got 3 that are already taken care of in this overlap. So the number I put in there is 4. And you can see if I add 2 plus 3 plus 4, I get 9. So that takes into account all the projects that he worked on. Now there's 0 projects that he may not, the other class he could have not written or produced, but done something else with songs. Maybe he performed or something like that. Those could go in the outside. So this number 0 represents the number of elements that are not in the 2 sets here, but could still be considered part of the analysis. For this one, it's 0, but in the other ones that we do, it won't be 0. So now we can answer these questions. Once we filled all these numbers in, all the little sub areas, and also this number in the rectangle, but not in the circles, we can answer these questions. How many projects did he write but not produce? Well, that would be what's inside this part of the circle. So he's written 5, written and produced 3. That means that he wrote 2 projects but didn't produce them. Likewise, how many projects did he produce but not write? So we go back to the Venn diagram and we see that there are 4 that are in this part of the circle for P, the P circle, and so the answer is 4. So by filling out the Venn diagram, we are able to answer these a little more obscure questions about the survey. So that's the basic idea. It just gets more complicated as we go along. So I'm going to erase that because I don't need that right now. Now, there's a formula that works when you have 2 sets that are overlapping. And it relates the number, remember, n of something means the cardinality. That's why it's called the cardinal number formula. Those are the number of elements in the set. So we're talking about cardinal stuff here, cardinality. And it relates the number of elements in the union of 2 sets to the number of elements in each set separately, and then you subtract out the number of elements that are in that intersection in the football-shaped area. So I've got this example. These are not numbers, these are actually elements. But if I were to draw a Venn diagram, instead of having the actual elements, just the number of elements, what I would do is I take this original diagram and I'd replace the actual elements by the number of elements. So I'm going to rewrite this or redo it. So there's my same diagram. This is still set A. This is still set B. What I would say is that there's 2 elements that are in the intersection, E and F. There are 4 elements that are in A but not in B. So A, B, C, and D are in set A but not in set B. And then I have G, H, and I. So there are 3 of those. So similar to the one I just drew, but this is going from specific elements. So actually, kind of there's a review. Set A would consist of the letters A, B, C, D, E, and F. And set B would consist of the letters E, F, G, H, and I. So and what I can say is that the number of elements in set A is 6. You can either do it by counting the number of elements in the actual set notation, or you can add these 2 numbers together. So it's 1, 2, 3, 4, 5, 6, or 4 plus 2, which is 6. The number of elements in set B is 5. 2 plus 3 is 5, or I can count 1, 2, 3, 4, 5. All the stuff we're going to do, we're not going to do this. We're just going to worry about the numbers. The number of elements in the intersection of A and B, which is this football, is 2. So what the cardinal number formula says is that the number of elements in the union of A and B is equal to the number of elements in set A plus the number of elements in set B minus the number of elements in the intersection. So I have all the stuff on the right-hand side, so I take 6 plus 5 minus 2 is 9. So that says that if I did the union of those two sets, that I should get 9. Now, you can just count them off the Venn diagram here. 4 plus 2 plus 3 is 9. What the formula allows you to do is to not have to draw the Venn diagram. If you just had the numbers, you could do it using the formula. So sometimes that's useful, sometimes it's just as easy to draw the Venn diagram and figure it out from there. We'll use this one more time. Most of the time we'll just do it visually using the Venn diagram. So I'm going to erase that page too. And I'm not going to talk about that right now. Delete that stuff. Let's get rid of that. Okay, delete that page. Okay, now I've given you guys a handout. Now, the people who are online, you'll need to just write these down. So that's what you get, the advantage of coming to class. So what you'll see is this handout. And we're going to go through 8 different situations. But let me explain what those numbers represent. So if I said, what are the number of elements in set A, I would add all the numbers that are contained in the circle A. So I'd have 8 plus 3 plus 1 plus 4, which would be 16. So there's 16 elements in set A. If I add these 4 numbers here together that are in this B circle, it would be 3 plus 2 plus 1 plus 0, which is 6. So there are 6 elements in set B. And then there are 4 plus 2 plus 0 plus 1 elements in set C. The footballs, this football, it represents the intersection of A and B. So here's A, here's B. This is the intersection. If you have sets A and C, this is the intersection, this football. And likewise, B and C. This little triangle-ish curved triangle in the middle represents where you have the intersection of all 3 sets. So what we're going to do is we are going to answer the questions about, we're going to figure out what area on the Venn diagram this represents, and then we're going to read the number that is associated with that. So what this is, the first one says we're looking at the intersection of set A and B, and then intersect with set C. So I'm going to do this on my thing. If you do the first intersection, it's this football. And then it says intersect with set C, so then I want to take whatever results from my first operation and do it again. So if I intersect this with set C, that gives me this little triangle in the middle. So that's what we just talked about. That's what the intersection of 3 sets represents. It's that little triangle in the middle. And the answer that we're looking for is how many elements of the total system we're looking at involves the intersection of these 3 sets. Well, it's this area, whatever that number is inside the area is the answer. So the answer is 1. There's 1 element that is in all 3 sets. We're not listing the elements. We don't care what they are. All we care about is the number of elements that share something in the proper order. So the way we would do this, showing it, we'd say, what is the cardinal number of the intersection of A, B, and C? And that would be 1. That's the number of elements that is in the intersection of all those 3. Okay, so I'm going to do one more, and then you guys are going to help me. So now we have the intersection of A and B with the complement of C. So if you remember the other day, when we had an intersection with a complement, that was the same as subtracting the elements that are in that set, that are removing the elements that are in the set that have the complement sign. So the way we did this was we said, okay, first we'll do this. We'll do this first. We'll find the intersection of A and B, which we just did a second ago. That's this part. So that's A intersect B. When you subtract it, you're removing the elements that are in set C. So I remove those. All I have left is this little shield. And then you look at the number in there. The number is 3. So the number of elements in the resulting set, which on the Venn diagram, so I'm going to write this two ways. I'm going to write it this way. I'm going to write it the other way, which is I replace the intersection of the complement with the subtraction sign. That is 3. So there are 3 elements. There are 3 elements in the resulting area that results from this operation. So I take A intersect B, which is a football. I subtract the area that involves C. That leaves me with 3 elements. Okay, so now I'm going to ask you to do the next one. And I kind of help you because the original expression is A intersect B complement intersect C. What we do is we change the order, so we do the intersection of the 2 first, and then we can subtract out the complement. So look at what I just did on the left-hand side, apply it to the right-hand side, and I'm going to ask somebody what the answer is. So I'll give you 20 seconds. So what you should do is look for the football that corresponds to A intersects C, and then remove the number that is in B. And the answer is timber, 4. Exactly. Okay. So what she did is she found this intersection, removed the B, the one that's in the circle B, that left this one right here. So the answer, the cardinal number of A intersects C minus B is 4. And so the last one is, even though this is in a different order, if we rearrange this, B intersects C intersect A prime, it's the one we haven't done yet. So the cardinality of that operation is harmony. Okay. What's the answer? It's 0. Okay, so how did you do that?
I do it the second way. I kind of just realized A prime, which means take away A, and now went over and down B and C.
Yeah.
And then I did the line.
Okay. So you didn't explicitly write it out. You realized that doing the complement was taking away. So yeah, you did it kind of in your head. So let me just, I can disconnect this now. I have enough battery power. So what you do is you're going to take the intersection of B and C. Here's B, here's C, here's the intersection right there. So I have a 1 and a 0. Then I subtract or remove the part that's in A. So this part is in A, this part's not in A. So when I remove that, I just have that left. So this is A intersect B minus C. This one's B intersect C minus A. This one's A intersect B minus A intersect C minus B. This is the intersection of all 3 of them. So now we have the 4 middle parts. Intersection of all of them. Intersection of 2 minus the third. Intersection of 2 minus the third. Intersection of 2 minus the third. They're all, you'd expect that because they're the same shape. Okay, next, moving on. So we have A complement intersect B complement intersect C complement. So now we have 2 complements in one set. So again, you can change the order. And so instead of starting with the intersection, over here we found the intersection and then we erased something. Here we start with, I guess what you do is you take the terms that don't involve the prime and figure out what that represents, and then you can subtract the other two, either one part or the two parts, depending upon what you're doing. So in this case, we take set C, that's right here, and the intersection of the complement is like erasing stuff. So if I take this whole set C and I erase what's in A, which would be these two, and erase what's in B, which is these two, so ultimately you take these three away, that leaves just this little part that looks like that. So the answer is 2. So the three outside pieces are one of the sets minus the other two sets. So if I took the cardinal number of that, I would end up with 2. So hopefully you can recognize which area that would be, the next one. So I'm going to ask Harley, so she's gonna, is it 8? Is it 8? Yeah, it is 8. Okay, so again, what you do is you take A, subtract what's in B, what's in C, that leaves this little bit left. So the cardinal number of that would be is 8. And the last, this one is the other one, right? It's in a different order. They're doing it in alphabetical order, but you know we don't have to do it in alphabetical order. There's no reason. So that result would be 2 because you take B, take out what's in A and what's in C. So we pretty much defined every one of these little areas. This is the intersection of all three. This is the intersection of 2 minus 1. This is, and then the outside parts are the set intersected with the other complements of the other two. So now we have all that. The only one we don't have is this one. That's the number of elements that are in the universal set but are not in any of the 3 sets that we have defined. So the way you do that one is the last one. So if you do the intersection of all the complements, so if I take the cardinal number of A complement, B complement, C complement, that's going to be equals to 6. It's that number right there. What's going on there? Well, you're taking everything outside of A and everything outside of B and everything outside of C and finding the overlap. And well, the only overlap is everything outside of all the circles, which is what that number represents. So I typically put a problem like this on the test. So hopefully you get what we're doing here. If you don't, make sure you come see me. Okay, so this is just an example. There's a couple problems where you use the formula. The difference here is they ask you to calculate the intersection, the number of elements in the intersection. The original formula that we just saw a second ago says the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection. What they're asking for here is the intersection. But just like any algebra problem, you know, you could think of you know, x equals y plus 2 plus whatever. You know, you can manipulate this expression. It's an algebraic expression. So I could solve for this. And the way you would solve for that is you want to get that on the left-hand side of the equation, and what's on the right-hand side of the equation, you want to get to the left-hand side of the equation. So if you remember from algebra, you just, what we would do is we would subtract this from both sides, and we would add this to both sides. So when I add these two together, I get 0. And when I add these two together, actually I got to add it both sides. I messed up there. Okay. So I have to add this to both sides. So I'm gonna subtract this from both sides. So the union part is subtract from both sides, and then I have to add this part to both sides. Otherwise, it doesn't work. Okay, so this is this minus that. So I've done the same thing to both sides of the equation. These two cancel out. And so it looks very similar. The equation doesn't change much, except I just switch this term with that term. So that's my original equation. That's my other other version of it. And so I know everything on the right-hand side, so just plug the numbers in. And if you do that, you get 7. So that's the number of elements that are in the intersection. If we did the Venn diagram for that, we would have, we'd have our universal set. We'd have our two sets. And this formula is actually pretty good because it's easy to go from intersections and then figure out the union at the end once you have it populated. But when you're given the union, it's not so easy to just do it. So I'm going to use the result that we got. It says there are 7 elements in set the intersection based on this formula. It says there are 20 in A, so if there are 20 here, what number goes right there? This is 7. The whole has to be 20. 20 minus 7 is 13. And then for B, the total has to be 12. I've already got 7, so I need 5. So you take 12 minus 7 is 5. And you can see if I add these together, 13 plus 7 plus 5, I get 25, which is what I originally started with. So this is accurately represents this information. And because I had the intersection and was able to fill this football in, it made filling the whole thing out much easier. If I tried to do it this way, it would take a lot more thought than I really want to do. Okay, moving onward. Okay, so what we've done so far is we have taken a Venn diagram that's filled out and answered questions relative to various intersections of sets and complements of sets, and we've found the particular number that applies. We're going to go the opposite direction here. I'm going to give you some information, and we have to fill in the Venn diagram. So it's like the first problem I think that we did. This one's fairly straightforward. This will be on the order of what you're going to see on the test. We're going to do another one that's a little more complicated, just to give you a little challenge. The first thing you'll notice is, well, the question is how many sets are involved in that problem? 3, A, B, and C, right? So there's 3 sets. Therefore, I need to draw a Venn diagram that has 3 sets. Now, it's not given that they intersect, but most of the time they do. The way you'd know they intersect, as you can see here, that there are numbers associated with the intersection of all 3. So we know we have to create a Venn diagram that has this characteristic 3-set shape. So we have our universal set. We have set A, set B, set C. And what we need to do is figure out how to put all the numbers in. So the first thing we're going to do, first thing you always do in these kinds of problems, and I haven't seen anywhere they don't give you this, is start with the intersection of all 3, because that is one specific area that's easy to find. So if we look on our given information here, all this stuff, we find that there is one of the statements involves the intersection of all 3 sets. That's 6. That number goes right here in the middle, 6. Okay, so that's step 1. Step 2, use intersections of 2 sets. So let's see what we have that's available. But before we do that, I'm just going to mark through that so I don't use it again. So let's see. Here's some information about all the elements in the set. This one involves the intersection of two sets. This one involves the intersection of two sets. And this one involves the intersection of two sets. So we're going to use those three pieces of information to fill in the next layer. And the next layer are these little places. So it's just like we did before. So let's try one and see if we can figure out how we fill the table out. So the number of elements in A intersect B equals 10. So the football, so these are footballs. I'll draw this as footballs. So we have the 3 footballs here, one there, one there. So if we know that the total in the football here is 10, we already have 6. That means the answer is 4. Yeah. Oh, sorry. So I'm going to write the other 2 down, and I'm going to ask you guys what the answers are. Okay. So we got 2 more things to worry about. So what about that one right there? The one right here. Mary Jo. 2. Yes, you're correct. I just want to make sure I was looking in the right place. So yeah, the intersection, this football is 8 total. So we have 6, so the 2 is there. And who else am I going to ask here? Jackson. What's this one? This little area right there. So we've used this one, we've used that one. So we got to use this one here. Okay, let me ask you a question. So the total in this intersection is 15. You agree with that? That's given. You have to agree with it. No, I was asking Jackson. So the total between these 2 has to be 15. If I already have 6 here, what does that have to be? I'm going to let Jackson answer the question. I know you know the answer. What's that? 9. Yeah, exactly. Okay, so we've taken care of those 2. So now we go to the top 3 stuff. So then we go to the what I'll call the basketball. So we just use entire sets. So that's the round stuff. And what do we know? We know, well, I'm just going to go over here. These are the 3 that we know. So if the total in this whole circle is 24, and I have 3 out of the 4 parts, I have this part, this part, this part, then you just have to add these together, subtract it from the total. So if you want to use your calculator or your head, not Melissa. Melissa's back there. Don't tell me. Sorry, I forgot your name. It'll come to me here. I'm getting there. Laramie. Laramie. So what do you think this number is here? Okay. If all of these add up to be 24, you take this number plus this number plus this number, which is 19. And so to get this whole thing to be 24, 19 plus what is 24? 5. So that's the answer, 5. So you can do it 2 ways. You can add these 3 numbers together and say, what do I need to put in there to make the total? Or I can take this number and subtract whatever's left over. So just, you want to answer, now you can answer. So how many are in this part that I haven't filled out? So it's 24 total. How many do I already have? Huh? So what's the total here? These three numbers added together. You do that in your head? 12, okay. So I need a total of 24. So how many do I need to put in here? 12, which is... No, you're the student. I know the answer. What's 12 times 2? 12. 12. Okay. So we got those taken care of. And let's see. James is over there. He looks like a good subject. So what is the number that needs to go here? So let's see. 15, 17. Yes, 9. So if you take 9 plus 6 is 15, plus 2 is 17. Subtract that from 26, you get 9. And then finally, we need to figure out what this number is here. So we're basically working through it. So we each one, so we know everything except one piece of information, and we can figure what that is. So if the total of all these numbers has to be 50, well, I know the total. I can find the total of every one but this little corner part right there. So if we add those together, and you just have to add them up. There's no way of, you can't take all this previous information. You just have to kind of count and make sure you include everything. What'd you get? Does it add up to 47? Okay. Everybody else get 47? You can use your calculator. Hmm? Yeah. Whoop. Yeah, this plus that plus that plus that plus that plus that. So there's 7 numbers to add together. 9, 18, 24, 36, 38, 47. So it is 47. That's the total. That is the number that you have in here. But it says that the total number of elements in the universal set is 50. So if there's 47 here, to get 50, you have to put 3 there. So this number is the number in the universal set minus the ones that we've already taken into account. So I'll write this out so you know explicit. So the answer is 3. What you do is 50, and then subtract the sum of all the other numbers that are already filled out. 1, 2, 3, 4. Okay, one more. What I do is I'm just counting the numbers so I get them all. I know I have 7 numbers. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It's easy to, forget where you are. And if you do that, you'll get 47. And so the number of elements, and what this is the number of elements in the intersection of all the complements. Do you remember that from the previous thing? If you take everything outside of all the circles, that's how you represent it. And there are 3 that work. Okay, so now we're going to do another one. This is problem 17 in your book. This is a little more difficult. It's not quite as straightforward, but a lot of it's the same, but there's some differences. Pardon me? Yeah, it's 16. So we do the same thing. If you go back to the previous problem, what did I say to do first? Start with the intersection. So do we see that in our list? Yes, we do. It's that. So that goes in the middle, 5. I'm going to tell you what people make, the mistake they make when they do these things. It's usually in the next step. Most people get the center right, but because they're not listening or they're asleep, they don't know. They just start filling stuff in. And so what people, the biggest mistake is they'll see the intersection of A and C is 13, and they'll write in 13 right there. They don't think that you got to take the difference. And I'd say half the people make that mistake. So I'm telling you now so you won't make that mistake. Hopefully. Doesn't always work. So this is the third time I've taught this class. So the first year you teach it, you don't know what people are not going to know. So then the second year, you're like, okay, I'll try to explain a little better what to do. And then the years after that, after people have made the same mistake, even after you've explained it differently, they still make the same mistake. Then the third year is you say, this is where people make mistakes. Yeah. Just so they overlap. Yeah, they don't have to be exactly circular. You just have to make sure that they, I mean, I'm lucky because I can draw circles with my thing, but if you're just drawing, and what in the test, I'll give you the circles. You won't have to make the circles, but if you're doing it for homework, just as long as. It might be. I don't know yet. I'm not sure. Okay, so anyway, don't just say, oh, it's 13, that's A and C, I'm going to stick that in there, and then I stick that in. You know, you got to do some calculations to get the next numbers. It's not that easy. Okay, so step 1 was the intersection of all 3 of them. So we knew that that was equal to 5, so we filled in 5. Now we go to the intersections. So in this case, there are actually only 2 of those. There's this one, and there's this one. You got to be careful. This is a union, not an intersection. So be careful about that when you make sure you pay attention. But anyway, has anybody put the new iOS 10 on your phone? Yeah, I did it. You like it? Yeah, I'm almost to the point where I don't swipe the screen. That's the one big thing that you first see is you I haven't actually done that yet. I have to try that. Oh, really? Okay. Well, you guys. Oh, really? Okay. You guys. Pardon me? I haven't actually heard that. It does take up less memory. That was one of the big things that I saw. It's like, all right, because I guess I have an 8 megabyte because I don't think they make it any smaller than that. So I'm always struggling with memory. Yeah, they don't, yeah, I asked them that. My daughter's looking at going to a different plan, but I was going to stay with Verizon, and I said, is there any way I can get more memory? And they're like, sorry, no more memory. Okay. So we're going to at least use what we have so far. So so let's call this the top, this the left, and this is the right. So which one is this going to help me solve? Left, right? Yep, because it's A intersects C. Don't put 13 in there, or whatever it is, 13. The total has to be 13. So that is going to be 8. It's kind of funny. It's kind of funny, but so I got my bachelor's in engineering, and then I got my master's in engineering. Then I went to work for a couple of years, and I had this opportunity. Let me finish my story first. Okay, so I had this chance. Well, it was when there was a recession. I'm like, I'm not sure if I'm going to lose my job, so I'm going to go back to school. So I went back to school, and I taught engineering classes at Tech. And then I graduated and had a regular job for many years. But it was the same kind of deal. I remember that. I was really bad the first year because they don't give you any training to teach when you go to college. You just basically, here's your classes and here's the syllabus, and you do it. But I remember after teaching the class maybe 3 or 4 times, it was knowing where people make mistakes and pointing that out. I think that helped a lot, and I think I got better. But anyway, that was. If you don't learn from people's mistakes, then go ahead, Justin. You were going to say. Huh? Oh, the next one's 3. And which one is it? The right one or the top one? Right one. Yeah, this one. Right. And you did that by looking at this. You know, the total is 8, so you have to do that. Okay, but we can't do the top one because we're not given any information. So now the question. Oh. And I did this wrong, I didn't fix it yet. This is actually the number of elements in set A. It's 15. I think that was that what I had, 15? I just didn't, I left out something. Yeah, I can't remember. Let me just undo it and then I'll redo it. 15, yeah, okay, sounds right. So now we got to do something, use one of the other ones. So what could we do here? I'm trying to remember how to do this. Because if you look at the first one, it says the number of elements in set A is 15, but I only know 2. The 2 I don't know, so I can't use that immediately. So that's not going to work. If I do this one here, this one is set A minus set B. So if I take set A and I subtract what's in B, does that leave me with just one unknown? It's this area. I know that the total here has to be 9. And I have 2 spaces, and so I should be able to figure out what that is. So that's the one I use next. You kind of have to go through them and see whether the information they're giving you is sufficient so that you are able to take the total and subtract what you're known and end up with the answer. So let me explain let me do that again. So if I take this one, this is what I'm going to do next. If I take set A, and I subtract the parts that are in set B, I end up with that. Notice I know this, I know the total, so I should be able to figure out what the last bit is. So the answer, let me undo all that stuff so I can get a clean piece. So this ends up being 1. Because 1 plus 8 is 9, and that represents this little moon shape with the cutout. So now I'm good shape. Does anybody remember what this is? Well, remember this. What area does this represent? The intersection of the complements. It's the outside. So that's 21. So we got that. So we've used that now. Let's mark out what we've used so far. We used that to get the middle. We use these 2 intersections to get these 2 pieces. So we've used that. We use this to get the 1 piece, and we got it. Okay. So now let's see what we got. Let's try one of the other ones and see if it helps us. So we got B minus C. So if we take set B and subtract C, that leaves those 2 places. So that doesn't help us any. That's not any good. I'll also use the number of elements in set A. I forgot about that. So I can mark that off already. I've used that already. No, I haven't. I haven't used that one yet. Now okay, right. So now we use that one because the other two didn't help us, because the first one was B subtract C. That was these two things. We don't know two things. The last one is B intersects C, and we don't know three things. So the only one that we have left, and I forgot about it, but it was the only one that would help us, is the number of elements in set A. So I've got, here's set A. I know 3 out of 4, so I should be able to figure out by subtraction. So the answer is, what's 15 minus 1, which is 14, minus 5, which is 9, minus 8, which is 1. If you add 8 plus 5 is 13, plus 1, and 1 is 15. So now I've got that, so that's good. So I've used that. How about, let's go back to what we were doing here. B minus C is this little bit, right? These two. So this plus that has to equal 3. Again, you take B, subtract C, that leaves these two. They have to add up to 3, so that must be 2. And then finally, we know that the union of B and C, which is this and that, have to equal 32. So what we would do to use this one, to find this one little area right here, is we take 32 and we add all the other ones up that are in both sets. So in set C we have 8, we have 5, we have 3. So those 3 plus those 2 right there. So you get 32 minus 16, 19. That's 13. So the answer is 13. So we've solved it. So that's more difficult. I won't put that one harder one on the test. I will not. People mess up the other one bad enough as it is. That would be a recipe for complete disaster. So, but hopefully, as you saw me working through it, you said, "Oh, okay, yeah, I wouldn't have gotten that without his help, but at least." Okay. Now I'm gonna do one here, and then I'm gonna hand out one that we're gonna work on in class. We may not completely finish it today. So this is just like the problem we worked, except that instead of just giving you the numbers, the numbers are going to have some practical significance. So what they've done is they have interviewed 140 people in the mall, and the results of the survey were 58 people use microwave ovens, 63 use electric ranges, 58 use gas ranges, and then we have the ands. We have microwave and electric ranges, microwave and gas ranges, electric ranges, and somebody had all 3. So we're going to use that information to fill out a Venn diagram, and then we can answer these additional questions just like we did in one of the earlier problems. So again, it's 3 sets: microwave ovens, electric ranges, gas ranges. I mean, ultimately you'd have the person's names, but in surveys we don't really care who the names are. We're looking for numbers. So the raw data might have names in it, or it may be anonymous. Subject 1, subject 2, something like that. So we draw 3 circles, just so they overlap. There we go. Okay, and we'll use a letter to represent whatever these sets are. So we'll use M for microwaves, G for gas, and E for electric. So just like in the previous one, we took the intersection information first. So which one of these numbers represents the intersection of all 3? Somebody said something. 1, yeah, all 3. So we can fill that in, and we'll put a check by it as we use it. So that's the first thing we do, intersections. So check that off, put the 1 in the middle. Okay, then we look for the intersections of 2. Well, here's these two things. So this is the intersection of microwaves and electric. The total has to be 19, so this one has to be 18. Okay. There's 17 people who use microwaves and gas ranges, so this number here has to be 16? Did I hear 16? I thought I heard 15. Anyway, 16, because 16 plus 1 has to equal 17. 4 people use gas ranges and electric ranges. Here's gas, here's electric. This is 1, so this has to be 3. Okay. And then we do the other ones are just the circles. So you might have to get your calculator out for this. Let's just move it up a little bit because I'm gonna write out what we need. I'll do the first one and then I'm going to ask you guys to do the second two. So let's do the microwave. I'm looking for a number to stick in here, so I take 58 and I subtract the sum of the other 3 that are in the microwave circle. So that's 17 plus 18, which is 35. So that comes out to be 23. So the answer here is 23. You can always double check by adding them back together, see if you get that. Let's try it out. 23, 39, 40, 50, 58. Okay, so that worked out. Okay, so go ahead and see if you can calculate what the other 2 numbers should be. If you want a little challenge, you can do it in your head. Let's see, Mackenzie's going to she's going to try to do it in her head. You already done already. Okay. So let's see everybody's. So Caitlin, did you have any? You don't have any. You're not writing anything there. Oh, you're doing it in your head. Okay. Have you got one yet? Either one of them. Just yeah, do the gas one. 30. Is that right? 38. Is it 36? Oh, gas. You're right. 38. Yeah, I was looking at the wrong one. 38. Okay. So what she did is she added these. She chose that probably because it added up to a nice round number. So 16 plus 4 is 20. 20 subtract from 58 is 38. Okay, Mackenzie, what'd you get? Huh? 41. So we'll add those up. 44, 45, 55, 63. So that's right. Just a little mental. You probably have mental math tricks too, but just got a little epileptic fit there. So the way I add these numbers up is I would add 41 plus 3, which is 44. 3 plus 1 is 4. And then I add one more, it's 45. Then I add the 10 first, so that becomes 55. I always add, when I add a new number that's two digits, I add the 10s first, which is kind of opposite of what you would normally do by hand. But it's easy to then just count up in the 10s, and then I add the other numbers. So if I was doing this one, I'd do 18 plus 1 is 19, 29, 35, 45, 55, 58. Or here I do 3 plus 1 is 4, 4 plus 16 is 20, 20 plus 38 is 58. So we'll talk about that in another class. There's this whole idea of Common Core, adding and subtracting with Common Core, and I get these things, Facebook things saying, This is why kids can't do anything these days, because they're teaching them these stupid, ways of doing it. I think mostly it's because you use calculators too much. That's the problem. It's not the way they're teaching it. And ultimately, when you do things, I didn't learn how to do stuff in my head. When I add these numbers together, when I calculate your scores, I go through and I add them all in my head. It's probably quicker than putting it in the calculator, because by the time I put in my calculator, it would, and then you can have the error of putting the wrong number in your calculator. So it's doing your brain. And what you end up, at least what I ended up doing, was using more of a procedure that you would call Common Core, because it's more mental things that you do mentally instead of writing them out. So okay, so now we can answer these other two questions. Exactly how many use exactly 2 of these kinds of appliances? So it says exactly 2. So which areas represent exactly 2 on this diagram? So this one, this one, this one. What about that one? No. So it's not in the middle, because that's 3. So it would be this one, and this one. So here we're using my mental math. 18, 28. Actually, I cheated that way. I went the other direction. 18, 24, 34, 39. So the answer would be 39. Those is exactly 2. So what did I get, 32? Forgot now. No, I got something else. What did I get? 39. It says how many uses at least 2 of these kinds? That would be 40. Because at least means 2 or more, and so you add the third, you add the case where you also use all 3. So there's some other, questions that you couldn't have answered by just looking at the original data. That's the whole concept here. So now you're going to write that down. I'm going to hand out the problem we're going to work on. That's not what I... Well, maybe we're not going to do that, because I thought I had another problem. What did I do with that? Well, we can still work on this one. This is the one we already did this one. Okay, I just made copies for no reason. Okay, well, plan B. So I was going to give you another one of these, but I forgot what I was doing. So anyway, those are that's the end of the chapter. We have 7 minutes left, so we are going to we're going to talk about the next chapter. What's happening there? Next, what is today? Wednesday. Next Wednesday. Oh, sorry. So what kind of problems? Ultimately, on the review, I'll tell you exactly which ones to do, but a lot of the stuff. Where's he going? Who knows? Oh, you have somebody you'd like to see? She is online today.
Okay.
Do you want me to? Let me see if she's still online. I don't see Megan online today. Yeah, give her a call. Okay. Okay, so we're going to open up chapter 3. So chapter 3 is about logic. And a lot of the stuff in logic has similarities to what we learned today we've learned about sets. Slightly, some of the terminology is the same, some of it is different, but they are very similar. So the whole idea behind this is not logic like using proofs in geometry. This is, it does have some kind of a relationship to that, but the ultimate goal would be to look at an argument of some kind. If this happens and this happens, therefore this final thing happens. And you know, what's the practical implications? Well, computers deal with that all the time. Even just in the addition and subtraction of numbers. So if you ever became a computer expert, you'd appreciate that. Even though when you use higher level programming languages, you do ask questions, logic questions. But even down to the nitty-gritty details of how a computer works, that also involves logic as well. Also, if you think about just functioning in a democracy, you have to listen to people's explanations of why you should support them, or you should go along with it, or why you should encourage your lawmakers to do something. And a lot of times, the kind of logic they use, if you aren't careful, you might fall for stupid stuff. So if you, yeah. So when we talk about people using faulty logic, you immediately think of Donald Trump in terms of their arguments about various things. And there was the latest. Well, it's every day, so it's not hard to find examples. But the the bombing in New York. Of course, it's Hillary Clinton and Obama's fault, and if you were like me, then that cherished thing would not have happened. Well, it turns out the guy who did the bombing was immigrated at 7 years old from Afghanistan in 1993. So obviously, Hillary Clinton was married to Bill Clinton, who was a new president in 1993, but there's no connection, and so there's such bogus, the logic, it defies logic many times over. The interesting thing, though, which you may not have realized, you probably know there were bombings. How many people have realized that there were? The ones in New York and New Jersey? You know about those? This last weekend, nobody died, so it wasn't, no, it was just 29 people were hurt in Chelsea. Well, that's the interesting thing. So it's the usual pressure cooker bombs and pipe bombs, which I'd be interested in seeing how those are made, but I'm not going to do it on the internet because I won't get in trouble. Like, what are you doing checking out bomb stuff? Well, that was the interesting thing. Each bomb, well, not each bomb, they were all designed in different ways. It was like this guy was saying, I think I'll make some different bombs and see how they work. So let me go set a few off, and then when I find the best one, I'll use it for the next go. And luckily, yeah, I mean, it was interesting that he tried lots of different kinds of constructions. I'm not sure what that means. Because some people said, well, that meant there was probably more than one person working on it. But he's a very interesting bomb maker, just because of the differences that he wanted to make in a bomb. Okay. Anyway, so I've rambled on enough now that it's the end of class. So we'll see you next Monday. You should read the news more. There's a lot of interesting stuff that's going on.